Ever wondered how a small startup or even a single developer working from a laptop can build an AI that recognizes cancer in medical scans or identifies rare plant species with 99% accuracy? They didn't spend 10 years training it. They didn't scrape the entire internet. And they definitely didn't have $1 billion supercomputer humming in the basement. So, how did they do it? They didn't build the AI from scratch. They borrowed one. In this video, I'm going to show you one of the most powerful ideas in modern AI. An idea that quietly powers all those successful computer vision systems that we are seeing today. Welcome to Schovia, where we make AI concepts feel like everyday ideas. Being able to train a successful computer vision system comes down to two things: legendary neural network architectures and not so secret cheat code called transfer learning. Think of it as borrowing the brain of a world-class AI and teaching it your problem in minutes. First, the ImageNet challenge that sparked the deep learning revolution. Two, these legendary architectures like AlexNet, VGG, and ResNet, and why they're different. And three, how transfer learning lets you skip years of training. By the end of this video, you'll understand how people get stunning AI results with shockingly little data, and why this isn't magic at all. Let's rewind to before 2012. Back then, computer vision was struggling. Researchers were trying to teach computers to see, but progress was slow and brittle and frustrating. Most systems relied on hand engineered features like edges here, corners there, a texture filter, hogs, etc. But then came the ImageNet. ImageNet wasn't just a dataset, it was a statement. It had 14 million images, 1,000 categories, and everything from a dog to a plane to a mushroom or a musical instrument, all sorts of things. It became the Olympics of AI, and every year the world's best teams competed on one metric: classification error rate. For years, the best methods hovered around 25% error. That meant that 1 in 4 images was incorrectly predicted. Then, in 2012, a team entered a model that didn't just win, it obliterated the competition. Error dropped to 15% overnight. The model was called AlexNet. And that moment, it didn't just win a contest, it changed the trajectory of vision systems forever. This is when something important happened. Researchers stopped talking about algorithms. They started talking about architectures, named network architectures, which are reusable blueprints, which have a shared design. This was the beginning of what we now call the networks with names. And you know what the best part about this is? These researchers shared everything: the code, the layouts, how they trained it, and all the model weights. Which brings us to the legends, which is part 2 of this video. Now here's where a lot of people get confused. They open a deep learning library like PyTorch or TensorFlow, scroll through the model zoo, and see names like AlexNet, VGG16, ResNet 50, ResNet 101, DenseNet, EfficientNet, and so many other models. And the question is, which one should I choose? And what's actually different about these networks? Before we answer that, we need to get one thing very clear. The real hero behind all of these breakthroughs wasn't a specific model. It was the convolutional neural network, CNN. Every architecture that started dominating the ImageNet challenge was built on the same fundamental idea. Let the network learn the visual features automatically using convolution. If you want a intuitive visual explanation of how CNNs work, or how filters slide over images, or how features are merged layer by layer, we have made a full video just on that, and I highly recommend watching it. Now, once CNNs proved that they worked, the natural next question is, how should we connect these CNN layers? And that's where these architectures come in. These famous networks aren't different types of AI. They are different design philosophies built on the same CNN building blocks. Think of CNN layers like convolution, pooling, activation, etc. as functions, and think of architectures as how many layers do you stack? How wide or narrow is each layer? And how does information flow between them? So let's make this intuitive. Think of a neural network architecture as styles of buildings. They all serve the same purpose, which is turning pixels into understanding, but they're designed very differently. So let's talk about AlexNet first. AlexNet was the first architecture to show the world that deep CNNs could be built and trained. In 2012, 8 layers was considered deep. And this network has 16 million learnable parameters. That's why AlexNet was revolutionary. Before it, CNNs existed, but on a much smaller scale. AlexNet stacked convolutional layers deeper than anyone had done before, and it trained them on GPUs, which was revolutionary at that time. It proved that CNNs can scale. Data matters, and depth of the network matters. But compared to today's models, AlexNet is like an early skyscraper, right? It's big and powerful, but it's inefficient by today's standards. Before we move on, there's one more nuance that affects how big a model is. Within each convolution layer, how many filters you have and how large are those filters? We call this the network's width. Basically, how many feature channels are flowing through each layer. And wider layers usually mean many more model weights. So the model's size and memory needs to grow quickly. Similarly, VGG didn't invent a new layer or something. Instead, it just asked a different question. What if we keep the CNN design extremely simple and just stack more of them? So VGG uses the same small 3x3 convolution filters, but repeated over and over, and it doesn't have any fancy tricks. It's just fancy stacking with no fancy tricks. It's pure CNN stacking. There was a 16 layer and a 19 layer version of this, and this meant there were 138 and 144 million learnable parameters in the respective variants of the model. This made VGG very easy to understand. It was very consistent, but it was very heavy. VGG is considered heavy because it keeps layers relatively wide and then adds massive fully connected layers at the end, causing the number of parameters to balloon into hundreds of millions. Think of it as a building that's made of identical bricks. It's beautifully structured, but it's massive. Note that when we talk about how deep a network is, we just usually mean how many layers have learnable parameters. We're not talking about pooling and activation layers at all. Now let's talk about our third network, ResNet. ResNet also did not change CNN layers, but it changed how they are connected. As networks got deeper, something unexpected happened. Training became harder, not easier. Researchers noticed that the initial layers did not quite learn anything. The layers closer to the output seemed to be the only ones that learned. This problem is called the problem of vanishing gradients, where the layers that are close to the input don't update themselves. The solution to this is skip connections that was first introduced by ResNet. ResNet allows the CNN layers to learn new features or pass the information forward unchanged. This made it possible to train CNNs that were 50, 100, or even 150 layers deep, resulting in models with parameters that were still in surprisingly manageable range, about 25 to 60 million range. Even with a much larger number of layers, parameters didn't explode because ResNet relies on small convolution filters and skip connections instead of wide layers or large fully connected stacks. So it's the same CNN, it's just a really smart way of connecting it. Think of it like adding elevators to a skyscraper, and suddenly the depth or the height of the building is not a problem anymore. So when you see these architecture names, remember that CNNs are the engine behind these. Architectures are like the wiring. They're all different, but they answer the same question. How do we best stack and connect CNN layers to learn from images? And this understanding sets us up perfectly for our final and most powerful idea of the video, which is transfer learning. Once you realize all of these models share the same CNN foundations, you'll understand why transfer learning works so incredibly well. At this point, you might be thinking, okay, this is cool, but I don't have 14 million images, right? And you're right. Training these networks from scratch would take massive data sets, lots of compute, and weeks or months of training. But here's the trick that changed this. CNNs don't learn everything at once. They learn in layers. Early layers learn edges, corners, and things like that. Middle layers learn textures, and final layers learn specific objects. However, edges are universal, shapes are universal. The way an AI detects an edge in a picture of a dot is the same as how it detects in an X-ray or a satellite image, right? Or an image of factory defects or handwritten digits. So why relearn those? Transfer learning is the process of taking a model that's trained on ImageNet and removing its final classification layer and then replacing it with a new one, which is suitable for your task. So you get the vision, but then you change the decision by retraining the final layer so that it's appropriate for your task. It's like hiring a world-class chef. They already have knife skills, heat control, flavor balance. You're not teaching them how to cook. You're just saying, here's our menu, which could be different from anything you have cooked before. And that's why, with this kind of transfer learning technique, even 50 images can be enough. Training can take just a few minutes, and results can be very good too. This is how most vision systems are built. This happens because pre-trained models exist. These are models that have already been trained on millions of images from ImageNet. Someone did the hard work once and everyone else gets to leverage it. So let's bring it all together. We started with the ImageNet arena, where the world's best researchers competed to build the smartest vision systems. From that came things like AlexNet, VGG, ResNet, all of these came, and each one used the power of CNN a little differently. And the real magic was not just that these models existed, but the fact that they are reusable, because in transfer learning, you don't need a supercomputer or millions of photos to build the classifier. You can leverage the learning of the giants who came before you. And here's the best part. Tuning a world-class ResNet into your own custom classifier takes surprisingly little code. I have a little Python notebook in the description below, which walks you through the exact steps to load the pre-trained model and point it at your data. You'll see that in just a few lines, you can harness the same power that won the ImageNet challenge. So building these models isn't a closed club for billion-dollar companies anymore. The blueprints are open, the brains are pre-trained, and the tools are in your hands. Thanks for joining us on Schovia Labs. Hit that subscribe button for more eye opening insights, and as always, stay curious.